To me, it's about fundamental science, fundamental questions, and fundamental curiosity. And what we're seeing with some of the so-called outreachers is that I think what they're doing is stamping out curiosity amongst young people. They Google questions about fundamental physics. And so what a teenager nowadays sees as one of the first hits are, Peter Woit, Hossenfelder. It's all this negativity, and that's very worrisome.
Welcome to Newsnight, the podcast where we delve into all things particle physics. Do you want to know what is going on at the Large Hadron Collider? Why scientists want to build new, massive particle smashers? Or how particle physicists are seeking to answer some of the biggest open questions about our universe? If you answered yes to these questions, then you're in the right place. I am your host, particle physicist, Dr. Sam Gregson. In this podcast, we will cover cutting-edge particle physics research, the fascinating future of the field, and interview active physicists attempting to unravel the deepest mysteries of our universe at the very smallest of scales. Welcome. Now let's get into the quantum weeds. What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a wonderful week and have a fantastic weekend in store. Now today, we're going to be discussing the divisive topic of string theory. The public perception of string theory is overwhelmingly negative. There have been hundreds of videos slamming the subject as a waste of time, a money drain, and a non-scientific pursuit that has stalled the field of theoretical physics. Everyone, regardless of their level of knowledge, seems to want to add their 2 cents on the subject of string theory. In this discussion, I want to hear the other side. Why are theorists still intrigued by string theory? And why does it persist? To help me understand the enduring appeal of string theory, I'm joined by a phenomenal special guest, Professor Thomas Van Riet. Professor Van Riet is a theoretical physicist at Leuven University in Belgium, where he specialises in studies of supergravity, string theory, holography, and cosmology. He is a staunch defender of free academic inquiry and believes that the messaging of several high-profile science communicators betrays a lack of intellectual curiosity and is having a deleterious impact on the image of various fields of theoretical and experimental physics. String theory detractor Peter Woit claims that Van Riet's main claim to fame is vigorously hyping string theory on Twitter. So who better to help me understand why theorists continue to see promise in string theory? So, hello, Thomas. Thank you very much for taking the time to come and chat with me today and answer the question, which I'm sure many people are interested in. Why string theory? So, before we jump into that, to Peter Woit, who is no doubt listening and very angry. Hello, Peter. I'm doing the experimentalist talking to theorist thing again. Please try to stay calm. It will all be okay. So, Thomas, Peter Woit, who is a well-known and long-term detractor of string theory, says of you in a recent article called Whatever Happened to String Theory, or based on a blog based on that piece, that Thomas Van Riet's main claim to fame is vigorously hyping string theory on Twitter. How do you respond to such a charge, and will you stop for Peter's peace of mind, if nothing else?
He's not wrong, but I hope it's not my main claim to fame. That's it.
It's one of them. One of them.
One of them. Then I'm happy, actually. Then I take it as a compliment.
Okay.
I hope I'm not selling propaganda. I think the propaganda is from the other direction. I try to bring some nuance. Yeah.
There is an awful lot, isn't there, just to set the scene of string theory bashing on the internet. This was part of the reason I wanted to chat with you today, is because what I see online on YouTube is incredibly negative. So I wanted to provide a space for you to give that positive message.
Right. So for me, honestly, it's not just about string theory. Because it would be a bit sad to just be there to defend a particular theory. No, yes. To me, it's about fundamental science, fundamental questions, and fundamental curiosity. And what we're seeing with some of the so-called outreachers is that I think what they're doing is stamping out curiosity amongst young people. And actually, I got very worried. To give an example, I mean, my kids are at an age where, they go online, they Google questions about fundamental physics. And so what a teenager nowadays sees as one of the first hits are, Peter Woit, Hossenfelder. It's all this negativity.
Eric Weinstein, whatever it
Exactly. And that's very worrisome. And I think we're underestimating the problem this poses. And again, to me, this is not about these debates, string theory versus whatever, loop quantum gravity. No, it's not about that. It's about really anti-scientific, anti-fundamental science propaganda, which we have to be, you should worry about it. Yeah.
Absolutely. So let's jump into the main event. So what is, for those who are out there who are non-experts, what is string theory? Is this how do you think of it? Is it a framework for doing calculations in particle physics? Is it a way to potentially quantize gravity? Is it, as many people would contend, a universal basic income or pension plan for theoretical physicists? What is string theory? Or maybe it's all of the above and more.
Right.
I'll give it to
you.
So
for sure, it's not the last thing you mentioned.
Right.
That's what it's what it's not, right? So
this is what we hear from a lot of the people that you
which
kind
is
of mentioned.
Amazing, right? So all of us researchers have.
What about your Ferrari, Thomas? I seen you, driving your Ferrari and going to Hawaii every day. And
yes, that's the money I get from Elon Musk for tweeting. Yeah. So string theory. So you can call it a framework.
Yeah.
Depending on the kind of questions you ask. So personally, I would regard it as a framework when it comes, for instance, to questions on quantum field theory.
Yeah.
I would call it a model when you think of quantum gravity.
Yeah.
Maybe this is a bit too technical. So maybe I can try to explain it a bit. So you said, is it an attempt to quantize gravity? So first off, very important, when we say to quantize a theory, it means that you have a classical theory, and then you say, let us make it quantum mechanical.
Yeah.
This is not what happened to string theory, or what string theory is. String theory is a theory where you say, quantum mechanics, quantum field theory, in the end, it says that particles are excitations of fields. So there is a notion of particle from the get-go. String theory is an attempt to say, let us just generalize this. String theory has particles, it has strings, it just has extended objects. So it's a very natural generalization of an existing framework of quantum field theory. Now, surprisingly, when you demand this, the quantum mechanical consistency conditions are so constraining that I would stop calling it a framework. So for me, the word framework is when many things are possible. Like we can say quantum field theory is a framework because I can invent many quantum field theories. And so, no, for string theory, not. Like, okay, there's some, classes of string theories, but mainly you could think of it as one theory. But when I say it nonetheless becomes a framework, is you can do with that theory many computations. And you can, it doesn't necessarily need to be about the actual universe we observe. You can try to solve computational problems in toy model of quantum field theories, and it gives you a new way to do these computations. So sometimes for mathematical tools, technical tools, sometimes even conceptual tools, in broadly speaking, theoretical physics, it's a framework. When you're interested in asking questions about what are the fundamental laws of the universe at the smallest length scales, then I would say it becomes an actual theory. Yeah. And I wanted to emphasize, and then I'm done. Sorry, I can talk sometimes too long. Is that I said what we didn't do in string theory is we took the classical Einstein equations, which describe gravity, and I said, let's make it quantum mechanical. No. As I said, we said, let us try to generalize this idea of the existence of particles. And what's completely amazing is that once you do that, and once you ask it a theory of, say, strings of one-dimensional objects or higher-dimensional objects, once you ask it that it's quantum mechanically consistent, it predicts the Einstein equations. So the Einstein equations come out as a prediction. And so you naturally have a quantum theory. Whereas other so-called alternatives, they tend to say, let us take that classical theory and let us try to quantize it. We have never done that.
This is the kind of thing that, Eric Weinstein will say with his geometric unity. Oh, look, in my framework, all of these equations come out, but you never actually see them come out. In string theory, they do actually come out from this framework. We have that contact with the old frameworks. So one of the most common criticisms we see leveled at string theory, it's always the main criticism, is that there's no experimental validation or verification. Why can't we get any experimental verification? And how do you respond to such a critique?
Yeah, so an important criticism. Well, so first of all, I think this is a non-stupid form of criticism.
Yes.
It's, I think, very valid.
A valid
and I appreciate, and I think every string theorist appreciates this criticism because we try to work with this criticism. But where all the fake news is on the internet is that this criticism applies to all theories of quantum gravity. Yeah. If there's something else than string theory, it just equally applies to it. So when you read the books of, say, Woit, Smolin, Hossenfelder, they're very wrong in that they don't admit this. But ask them for a possible alternative theory of quantum gravity, which does make predictions at easy, accessible energy scales.
At the TeV
right.
energy scale. Or whatever.
Obviously, their answer will be no, because we would have already seen it. Yeah. Or we will know it in 5 or 10 years from now. No.
So if you're going to do this work, this is just a problem that nature throws at you, right? Where we're dealing with incredibly high energies.
And in that sense, so imagine loop quantum gravity is a consistent theory of quantum gravity. It for sure has that problem. And I would say the good news is that string theory, in my opinion, gives more hope. Gives more hope that we do not have to jump into a black hole to discover what are the laws of physics. Because that actually, it is an experiment we can do. It doesn't cost a lot of energy. We decide to jump into a black hole. You hope you don't spaghettify, which is okay. If you jump into a big enough black hole, you will not spaghettify at the horizon. And you will be able to see what are the actual laws of physics, but you won't be able to tell it to somebody else, right? So that's a clear low energy experiment that will settle what are the laws of quantum gravity. Unfortunately, nature has played a trick on us. If you have access to it, you will not be able to tell it to anybody else unless they jump with you into the black hole. So maybe we can all jump into a black hole.
Maybe that's where we can put the communicators that you were talking about. They can go.
It's not a bad idea, and then they see the strings, and they will be very unhappy. But sorry, I think I lost.
You said this was
the energy scales, right?
The energy scale.
So yes. So the fact that, I mean, this is something in physics called the decoupling principle, right? So, and the decoupling principle essentially tells us that if we want to see effects of quantum gravity, most likely it's going to happen at a very high energy scale. And I say most likely because it's tricky. Yeah. Okay. So, but the standard thing is that yes, any quantum gravity effect is suppressed by a number. And the only way then to get that number to become big enough so you can measure it is that you put in the energy in your detector, in your experiment, whether it's a particle detector, whether it's some cosmological experiment, you name it, right? So, but where I get more enthusiastic about string theory in this regard is that the standard law is that it's the Planck energy scale that sets the effects of quantum gravity. Yeah. So for those people who don't know it, like the Planck mass, so mc squared, a mass is an energy scale, right? So this is essentially 1 divided by Newton's constant of gravity, which is a very tiny constant. So 1 divided by it is a very big number. And this is why the energy is so big, right? So the fun thing is that string theory doesn't come with the Planck scale. It comes with another scale, the string scale. And the string scale is a scale at which, if you would have energy of the order of the string scale, you would see that a point is not a point, but a string or some extended object. That energy scale, if you would do the computation in string theory and you compare it to the Planck scale, it's typically well below. But if you ask me, Thomas, so what's the number? So I cannot tell you the number.
Yeah.
I can tell you it's typically well below, but to fix that number, I need to fix a ground state of the theory. It's like, right, it's this issue of the landscape. So this is nothing particular to string theory, but if you have a fundamental theory, It doesn't need to be a theory of the universe, something that's very fundamental. And you want to, that means a theory means that you have the equation for it. And then you want to say, what does it describe? It never describes something uniquely. Okay, so a model in physics, it usually means that we say the words, you give a Hamiltonian, and that means like a function that describes how the energy of the system looks like. And then to know what it means when it's realized in nature, you need to look at what are the lowest energy ground states, because everything in nature, as we know, wants to go to the lowest energy state. So our universe, as such, is like an excitation on top of a low energy state. Good. There's not a single model in physics where the low energy state is unique. And the more simple the theory, the more simple the equation, that's the bizarre thing, the more crazy ground states you can have. And this is, by the way, this is, by the way, the original criticism on string theory by Smolin, Woit, Hossenfelder. And it's insane because this criticism applies to our own standard model of physics, which they all agree is a good theory of nature. So our own standard model has almost an infinity of possible ground states. And we can do calculations with the standard model because we have actually figured out which of the ground states we're essentially in. Yeah. Right? But this is not so easy for string theory, but it's more a computational problem, right? So, it's an observational problem. It's not a computational one. So that's what I wanted to say. And so depending on which ground state of the theory I have, the energy scale at which I would see indeed the effects beyond the standard model of particle physics, that energy scale, it depends on the ground state. Yeah. And I do not know the answer to it. Yeah. The only thing I'm saying is I'm getting excited because I think there's more and more evidence brought by something called the Swampland program, which is telling us that maybe like the scale of quantum gravity is surprisingly low. Is surprisingly low. And so there must be kind of light particles out there beyond the standard model, which are predicted by quantum gravity theories like string theory. And there should be for sure light enough so we can make them in a lab. So right, I need mc squared of energy, and they're light enough so that we have access to that amount of mc squared. So then you can ask yourself, why haven't we seen them? We haven't seen them because, not seeing something in physics has two reasons. Either the energy required for it is too high.
Or it couples very, very weakly.
Exactly, couples very low. And so when we look into the sky, we see that the universe is dominated by dark matter. We see that. Yeah. What is dark matter? The fact that we don't know is because it couples ridiculously weak against the stuff that our bodies are made of and our experiments and our detectors are made of. So we see that our universe is filled with stuff that somehow decides to not couple to the material in our detector.
I mean, look at the neutrino. We couldn't find the neutrino for decades, right?
It's an excellent example. And by the way, surprisingly, the neutrino mass scale might even be, according to some models, even a mass scale of quantum gravity. So just to show you how much it can go down. And I think a dark sector, we call this a dark sector. It's a sector that somehow is light, but it couples so weakly to our own sector, meaning by sector, I mean the stuff we're made of, that it's very hard to detect. It's a common thing in if you build like models in string theory. By models, I mean if you look at ground states of the theory and you look at what kind of theories it describes, right? So then you see that there's nothing strange to have a dark sector. So maybe the answer is the quantum gravity scale is low, it's out there, but we just have a hard time measuring it.
So there's some hope that we might be able to get to this scale in a reasonable time scale in a reasonable future.
But I must also say it could also be not the case, right? I personally, I don't want to make a bet.
Yeah.
But it's good that the history of physics has shown us that optimism is a must. It's a duty, right?
Yeah.
And what we see in those science outreachers is that they very much do the opposite. It's all about pessimism and then framing people in academia as people that go for the money. Let me make this also clear. Maybe I'm bragging about people in our field, but all of us could earn 4
Much
times
more
the
in
salary.
a bank, yeah. We'll go working in a bank or something.
Bank, AI company, like actually the people in my field that quit either because they have to quit, they don't find another postdoc, or they decide to quit. I know many of them, they're all like, their salaries, I can only dream about those, right? So no, when we stay in the field, we decide to not have such salaries. Let that be clear. So it's complete bullshit. Sorry for my language.
So this is, you kind of allude to it there, but a slightly sort of controversial or inflammatory follow-up. So what these communicators will say, and this is kind of the kind of Hossenfelder line, would be, given that all these hypotheses and frameworks attempting to quantize gravity suffer from these similar experimental constraints, should we even be trying to pursue this right now? Is it simply too difficult? We're not going to get any experimental verification. Should we even bother? And you're saying this is a matter of fundamental curiosity, right? We should still try, even if we're uncertain that we will get this verification. That seems to be where you stand.
But of course, there is a extremely nuanced debate to be had, and probably that doesn't sell on social media.
Yes,
right.
Of course,
so everybody understands taxpayers want their tax money. It's not nice to give money to taxes, and we need to think wisely about what we do with this amount of money. Yeah. And so, of course, I don't know of you're a particle physicist. I don't know of a single particle physicist who says like, oh yeah, let's build like another largest possible collider. It's like, everybody's like, no, we have to think very careful about it. What kind of collider? Yeah. What parts of the world? Who's going to pay for it? Yeah. Everybody's very nuanced about it. Like, should we give money more to the gravitational wave experiments, or should we go to particle detectors?
We have the European strategy. We have P5, where there are months, years of discussion about how we should spend the frankly insufficient amounts of money that we're given from the government on what experiment. That these decisions are not made at the drop of saying, look, oh my God, build this massive particle collider. We'll all make loads of money. It is such a stupid canard. It's just ridiculous.
Absolutely. And also there you can actually see, if you look for their arguments by these science communicators, if we should call them always like that, where they claim we are making a mistake, or mistakes have been made in the past when it comes to arguments in favor of those colliders, that's where you can see they're against curiosity. So the arguments we used in the past, they're not watertight. So one of them is called naturalness.
Yes, of course. Yeah.
And naturalness means it's not a real mathematical principle either. And it's a difficult concept to explain if you're not working on theoretical physics, but I'll make an attempt. The simplest thing to say is that naturalness is telling you when a certain number is very small, you should ask yourself, is this by accident, or maybe there's a reason for it?
Or is there some cancellation that's causing it to happen?
Exactly. So it's an invitation to be curious. So to give an example, if I walk through the forest and I see 20 rocks piled on top of each other, and I know, how lucky can you be? Yeah. Like, how much fine-tuning is needed to create this? I should think who did this?
Yeah.
Of course, you could say, no, it can have happened by accident, just some fluctuation in nature or whatever. Sure. I think humanity should be the person in the forest that says, what happened here?
Yeah.
And they're saying no.
This is where I have a really big problem with so what, for example, Sabine Hossenfelder will do is set these arbitrary lines of what she calls pseudo problems or proper problems. And she will say, look, I have the standard by which you are allowed to do problems, which, as you say, cuts off curiosity. Okay, maybe you're right. Maybe, the Higgs is light just by chance, or there's some other framework that we don't understand. But given that we have a really good framework of quantum field theory that has worked in the past, and it's telling us something looks weird, it's worth examining that idea, right? It's, maybe it's not, but it's a potential standard that can help give us a way forward when we don't necessarily have a clear path to go with at the moment.
Exactly. And even asking the question, so people often draw the analogy with a much older problem, or a problem from many centuries ago. I think it was mainly attributed to Kepler, Johannes Kepler, So he's the one who understood, at least found some phenomenological laws that describe planetary motion. And it was only Newton afterwards who had a fundamental theory who could explain those laws, right? Newton mechanics. But Kepler, of course, when he understood those laws, he already realized, like, well, we're lucky that we on the Earth are at this distance from the sun, because, according to my laws, other orbits are possible. And if we would be too close to the sun, we all die because we get fried. Or if we're away, we all freeze to death. So Kepler was like, okay, my goal in life is to calculate the distance from the Earth to the sun and try to calculate that number out of some fundamental principle. So people like Hossenfeller maybe or others, they could say, this is what you guys are doing. And it's the wrong question. Kepler asked the wrong question. Now we know he asked the wrong question. Why? And that is that, according to Newton's laws, the distance Earth-Sun is just an initial condition set by the cloud of dust that collapsed and formed the solar system. And we know because, well, we understand Newton mechanics, but also we now look into the sky, we see other stars, other planets, and indeed, distances between a planet and the star can be whatever it is. So it's more of an initial condition. But Kepler still asks a good question, right? And to believe that, so of course, from a point of view of any fundamental theory, to some extent, the mass of the Higgs could be like that, but not entirely, right? So I think this is also the nuance they don't want to explain, is that we don't have to talk about string theory, but any other theory that has a multitude of low energy states or stable configurations, let me call it that way. There will be configurations of a theory where the Higgs has a certain mass and another mass, and depending on the vacuum you find of the theory. And then you could say at some point, okay, if it would have been another vacuum, we as humans would not have been alive. We could not be here, and we could not ask ourselves a question. But you see, it means that the answer is somewhere in between. It means that not any mass of the Higgs is possible, and it's definitely a good exercise to try out to find out what are the possible masses by understanding the fundamental theory, and then try to understand correlations. Like, you observe the Higgs mass. Could the Higgs mass somehow be related to, I don't know, some other mass, some other coupling in nature? And in fact, if you take a typical vacuum of string theory, and I'm saying string theory because it just allows us to do these computations, we typically get things like Higgses, all these couplings that we know in standard model, we get them. And they're never unique, but we see so many correlations between them, right? So it opens sort of the possibility that we might be able to explain on a fundamental level certain parameters in the standard model. And so we should be curious about them. We should not just throw our hands and say they're God-given. Let us stop thinking about it and do something else with our life. No, we should be curious and keep on being curious and build machines to sort of understand what can we find more. Yeah.
So one of the things that people will say is that string theory is, and this is kind of shaving off more into philosophy, I guess, is that string theory is not science because you can't do that testing. How do you respond to that? And does it matter? Because I get the sense that a lot of people seem to take the development of theory for granted, right? That one theory, geometric unity and string theory, this was Hossenfelder's line to defend Eric Weinstein. They're basically the same. They're both just castles in the sky. You can't test them. So there's no difference between them. Does it matter?
So
is it science?
This is crazy, right? I mean, it's even difficult to answer this question because it's so annoying to have to answer it. So I have two answers. So one very quick, we already discussed.
Yeah.
Yes, there's an experimental window into string theory. And it's just a matter of energy scales, and we need to understand it better.
Yeah.
And patience is an important thing. I mean, it took us so long to find the Higgs, right? Okay. My second answer, I think this is the one point that I feel lacks in science outreach everywhere. So, I mean, I used to be a big fan of Stephen Hawking's book, the usual books at my time, Michio Kaku, Brian Greene, you name it. Penrose, whatever. And I feel many fail to say the following simple fact. once you ask for a theory that it's valid at all energy scales, the logical consistency that this requires is extremely constraining, and it's difficult to explain to people who don't work on it. But let me make a bad analogy, but to some extent, it's actually.
But it has to incorporate everything that's gone before as well, like into its framework, right? It's already constrained by what has gone before. It has to explain those things that have gone before already.
Right, but even if I don't ask that it has a standard model of physics, let me say that I don't even ask for it.
Okay.
Even just a mathematical requirement that I have a theory, which, mathematically speaking, has a spin 2 particle, meaning a graviton gravity, that you insist on the laws of quantum mechanics to still be correct. Yeah. And then you just ask things, okay, this is more an analogy, to some extent is correct. I don't want to be able to build time machines. Because if I can build a time machine, it's crazy. I can kill my parents before I was born, you name it up.
So you want whatever this new theory is to apply, to be constrained by certain physical laws that we believe continue to hold.
Right. And I actually remember this was one of the things when Sean Carroll was in a debate with Weinstein, then he actually mentioned this. Like, does your theory even, is it even consistent at the mathematical level? Do you have anomalies and so on, right? So the guy clearly doesn't know what he's talking about. Yeah. So, and this to me, I just want to make this absolutely clear.
I think he even asked Joseph Conlon to check that for him. To can you check if it has anomaly? It's like, dude, what the fuck?
Exactly.
Yeah, you don't even know that you need to do this, or how to do it. And yet you're out there saying that you've yours is the greatest theory. Anyway,
right. Exactly. No, absolutely. And so I just want to give the message out there that this is absolute science. So you can try to, as an exercise, to say, I want to write down a theory who can do this, this, and this. And if I then say, okay, with all these principles, I almost get to a unique answer. It doesn't matter whether you can already test it or not. That by itself is an extremely non-trivial exercise. Yeah. And let me give you one famous example, which I think to me has been sort of one of the reasons I fell for string theory is that, so this is a famous example, I think started with Stephen Hawking and Wittgenstein, that the laws of gravity, they're very similar to the laws of thermodynamics. And this led Stephen Hawking to say, well, it looks like it very much that the area of a black hole is proportional to the entropy of a black hole. And of course, in relativity, that's impossible, because entropy means that if something has entropy, it means that there are many possible states that look the same from a distance. Like we say a gas has a certain temperature, volume, pressure. But then there's so many possibilities of arranging molecules in a gas that give rise to the same volume, pressure, and temperature. And so, but for a black hole, no. In the classical laws of gravity, there's only one black hole solution. It doesn't have, there's just charge, spin, and mass. That's it. So it cannot have entropy. Yet Hawking finds, and he does calculations like this thing behaves like it has entropy. And of course, people said, sure, but then it's a theory of quantum gravity that should explain the entropy. So if somebody ever claims to have a theory of quantum gravity, what they should do, they have to do a test case. They construct a black hole solution in their theory, and they're going to count the quantum mechanical microstates, like the possible ways of putting molecules. And so in string theory, it's super hard to do this. But thanks to work, for instance, by Strominger and Waffa and others, they made some example, which of course they criticize, I'll tell you later about it, where they know how to do that calculation. And there's no reason that calculation will ever give you the entropy of a black hole. But okay, they set it out, you do it. Long calculation, very smart tricks. And what do they get? On the nose, like the factor matches. It's just insane. If you look at the calculation, it's just insane. So the factor when I'm talking about these details is that the entropy of a black hole should be in the certain units, the area divided by 4. They exactly get that number 4. Like they get the area and then they get the 1/4. It never had to happen. You have to understand that if you do something where a number equals another number, and there's absolutely no reason for it, you know that there's something deeply correct about it. It even can be so that string theory doesn't describe nature. I'm fine with that. But to me, it shows that it has passed the extremely hard logical consistency test of being a theory that describes gravity in a quantum mechanical way, right? And I think physics is full of theories that we know might not actually correspond to the real world, yet we keep on studying them. And another example I always give to them is the Ising model. Every student in physics has to study the Ising model. We all have to. And the Ising model is a theory of like arrows pointing up and down with little force between them. And we like it because it's a calculable model. We can see phase transitions like we see with actual magnets in nature. And everybody agrees that there's not a single magnet in nature that is given as described by the Ising model. We still, it doesn't matter. So for me, I always said it, even if somebody has approved that string theory doesn't describe our world, I honestly don't care. So, I mean, of course it's bad news, but it's still extremely useful. It's like a theory where you can at least answer your questions about how would a quantum mechanical theory of gravity work? How would it deal with a Big Bang singularity? You name it. You can test that with string theory.
So this is kind of what I wanted to get into, and you've touched on one of the points already. Is why is string theory the most popular, the most promising framework for quantizing gravity? What hoops has it jumped through that other hypotheses have not, and why are those hoops so important? Why is it, for want of a better words, better than those other hypotheses? And why are we still doing it? So you mentioned it allows these calculations of the entropy of a black hole to be done, for example. That seems like something it shouldn't be able to do unless it has some deep connection to quantum mechanics and gravity. What other mathematical consistency tests has it passed that we think of it as a promising framework? So you mentioned, for example, anomaly cancellation. That seemed to be the thing that kicked all this off, right?
That's the first string revolution, right? Without going into details, there are like 5 string theories, which in the end seem to be different sides of the same coin. And then in the first string revolution, they had access to sort of 2 of them. But then those guys had, I don't want to get into too much mathematical detail, but they had things which are called gauge groups. And gauge groups we know nature is described by gauge groups. Like it's a mathematical thing, and the standard model of particle physics is built on this. And we already knew that you cannot just have any gauge group. So for instance, the strong force is given by something that's in mathematics called SU3, the weak force SU2, and so on. And so the moment you have a theory of fermions and these gauge groups, we know that you can write down many classical theories, and then you can quantize them, and you know that it typically fails, meaning that these theories are not logically consistent once you have them quantum mechanically. So with these first string theories, they saw these gauge groups, and are like, yep, this is going to kill it, because we have fermions, we have gauge groups. It has to be a miracle that this thing works, because the consistency conditions are very constraining. And as I said, they didn't have any choice. Like in particle physics, we say, to not have an anomaly, we just need so many fermions, this kind of gauge group, so let us take it. No, they didn't have that choice. Like it was given to them. Let's now hope the anomaly cancels. And then so what was a tough calculation, and they find it cancels. Like why? I mean, it just does, right? So, and string theory is full of those things where you're like, okay, my God, if this doesn't happen, the theory is just wrong. And when you do the calculation, there's no reason. Like you don't know, like you never fed in the information. So it could just give you the wrong result. And every time we do these computations, every time it works. Right. So at some point, that's why many people, we say, you're religious. But you see the thing on a daily basis being so like people say the word beauty, but it's more like, wow, this Joe Conlon
how could it look this
nice.
Wonderful if it wasn't God? How could it be look? Yeah.
Right. I think it was Joe Conlon who said, you have the feeling that this thing that you work with outsmarts you the whole time. And I think maybe it was Witten who once said, I'm not sure it was Witten, but somebody said, string theory is like coming from aliens, and they gave it to us 100 years too early or something. So we're still always all amazed when you try to work with it. But so you asked, how does it differ then from other theories? So first of all, I do want to give some credit to criticism, which is, I think, criticism by Smolin, Rovelli, which does make sense to me, is that you have to, of course, be careful for a sociological sort of dynamic that if more people work on one theory, that theory will be more mature with respect to another one.
Yeah.
And then if it's more mature, it's going to attract even more.
Yeah.
You can have, sort of a self-amplifying effect.
Yeah.
And everybody acknowledges that, right? But I would say loop quantum gravity, it's still very fundamentally different. So again, as I said, those theories are much more in the spirit, let me take a classical theory and let me try to quantize it. And as I said, string theory is not that. It's just like gravity came out. We never asked. By the way, string theory was developed not to describe gravity. Yeah. I don't know how many people know this. Yeah. It was invented to describe the strong force. And then they realized in the strong force that there must be some kind of a string, which actually we have observed today. It's called a QCD string. This thing exists. And this string has a spin 2 fluctuation. And so people are like, oh my God, we get a sort of fundamental spin 2 fluctuation, which is like a graviton. Right. So, and then they check the equations of motion that a graviton has to obey. In the classical limit, they exactly get Einstein's equations. In the same way, let me also emphasize that it's not often mentioned. So in fundamental physics, there are like two kinds of equations. There's the Einstein equation for gravity, and the equations for the particles, it's what I said, it's like this mathematical thing called gauge groups. The word is Yang-Mills theory. Yeah. So their equations called the Yang-Mills equations. Yeah. They're very beautiful mathematical equations. Also so string theory, you never put in the Yang-Mills equations in string theory. You never. You just ask, I have a string, and gravity is a closed string. These Yang-Mills equations can be, for instance, described by open strings, but also by closed strings. Anyhow, you put it in, and what comes out? Yang-Mills equations. We never asked for it. It came out like that. Yeah. Right. So I think that's an extra asset with respect to attempts for alternatives. Yeah. And also, as I said, like this consistency test, for instance, the claim is that in loop quantum gravity, they can get to A/4. So that entropy of a black hole is entropy divided by 4. That's actually not entirely correct. They can get it by fixing another number. So they have to fix another number to get it. And then there was a beautiful paper by Ashok Sen, which somehow has been ignored. I don't know why. I think because Ashok Sen is an extremely modest person, very polite. He doesn't want to upset anybody.
He's not pushed it enough.
Yeah, so he said, okay, but let us do another test. So once you guys fix that number, well, the formula for the entropy of a black hole actually contains some extra terms which are much smaller. We call them corrections. They're sort of quantum corrections. And so Ashok Sen said, let us calculate the first number, the first such correction. And also there, if you want consistency, this number has to come out in a specific way. Yeah. So Ashok Sen said, okay, let me try to do it for string theory. And he knew this can go wrong. So the guy, was playing a dangerous game. He does the calculation, works out. The number works out, super happy. Again, a non-trivial consistency check. And then he does it for loop quantum gravity. And guess what? The number came out wrong. Yeah. And since then, that paper has been out there. And I personally have never seen somebody from the loop quantum gravity community even addressing it. That's a bit bizarre. Yeah.
Interesting. What about this? We hear a lot about this ADS-CFT correspondence. Yeah. What's that, and why is it such an idea in favor of string theory as well, that we're onto something?
Right. So this is an example where I say that string theory becomes a framework because it can help us also understanding other branches of theoretical physics or even mathematics. Right. So I think, so that's one of these healthy signs of a theory. Like, I think it always has happened in the history of science that when somebody made a big discovery, it usually had more impact than the field itself. Yeah. And so string theory has given us ADS-CFT, which, by the way, I also want to emphasize that the bigger umbrella of ADS-CFT is called holography, and it was something that was already postulated before string theory came about. So it was already an idea by 't Hooft, by Lenny Susskind and others, and it is related to the fact that the entropy of a black hole goes with the horizon area. Yeah. It's not obvious in physics that you can say that the entropy of a ball of stuff doesn't scale with the volume, but scales with the area. Yeah. And they were like, my God, if it scales with the area, then, a theory of quantum gravity has to be very bizarre. Yeah. They say the words in the communities, extremely non-local.
Yeah.
Like the degrees of freedom of a theory of quantum gravity are not like local points. They must be so non-local that the degrees of freedom can be described on the boundary of that space. I know it's a very abstract thing to say.
Yeah.
And then came Mallasena in the end of 97, and he, by just playing with things in string theory, he suddenly realized he could make it extremely precise. And so string theory then gave a very concrete mathematical framework. There's literally a mathematical formula that allows you to make this idea of Susskind and 't Hooft precise, and you can then do calculations with this formula. That means that let me give a practical example. You want to study a four-dimensional particle physics theory at a finite temperature, because that's what happens inside a collider. There's a plasma at high temperature. Turns out that with this ADS-CFT correspondence, you can map that to a problem, very abstract, of five-dimensional gravity with a black hole. That's like exactly like in the picture here.
Yeah.
Okay, so this black hole gives us, anyhow. And so one of the amazing things is that when we can do these computations, we can reproduce all these non-trivial things in quantum field theory. So in quantum field theory, one of the big problems, you still get millions of dollars if you can find analytic proofs, is that quarks confine, right? And it's super hard to mathematically prove this. The great thing is that now we can put Yang-Mills, so these theories on a computer, and these computers can do extremely non-trivial calculations, and then they seem to show quark confinement, right? So with ADS-CFT, this is a classical problem, classical gravity, and you can actually, students in Leuven in our course, they can show quark confinement. Like it's extremely powerful. Yeah.
So that's what I wanted to get at. The next thing was that do we have any practical applications of string theory we can point to? So you seem to be saying we can do these calculations potentially in gravity. Yeah. We've got ADS-CFT calculations in plasma physics, and also in and condensed matter physics as well.
Right.
Are these?
I have to be careful that I don't become spread propaganda either.
Yes,
so
of course.
I need to
we want to get things correct.
Yeah. So I need to bring the nuance. So when we are able to do that calculation, namely we map a problem in field theory, in particle physics, to a problem in gravity with one extra dimension or more dimensions, or the other way around, it's not so easy to map it to an exact problem that we encounter on a daily basis. So I'm not sure. I hope I don't get too technical. So let's say to understand what happens in particle colliders, you need to understand theories with what you could say 8 gluons, right? So gluons are like the force carriers of the strong force, like the particles that carry the strong force. And you could say there's a way to claim that there are 8 of them. Okay, so good. So what does ADS-CFT do for you? It allows you to do extremely non-trivial calculations of theories with gluons. And these are calculations you will never be able to do with quantum field theory techniques. But the number of gluons that you typically, like if you want to be able to do the calculation, number of gluons that you have is rather of the order of a billion. You could say, oh my God, this is not at all realistic, or it doesn't even come close to reality. That's not true either. It was already Gerhard 't Hooft understood before string theory that a theory with 8 gluons is not so different from a theory with 100 or 500, especially when it comes to certain things like do quarks confine or not. The moment I have 8 or more, you expect the answer to be yes. Other things are like phase transitions in these theories at certain temperatures, like confinement, deconfinement scale, and so on. So we can do these computations, but we can do them typically where we say, okay, the number of gluons has to be large, and then so then if you want to then apply it in our world, you have to make sure that you ask questions which are not so sensitive to the amount of gluons that you have in a theory. And these questions, they exist. And on one of them, there have been applications to like the behavior of plasma, where there are claims that you can, find certain bounds on viscosity and you name it very quickly from the string theory calculations, right? But I must say, we have to be honest that it's very similar to, it's not a problem of the theory, it's a problem of us humans that want to work with the theory, right? So as I said, so string theory, we can find many ground states of string theory, gives us a lot of particle physics theories, but to find the one that exactly corresponds to our universe, it's very tough. But it's us, because we're not good at mathematics. And the same is true for ADS-CFT correspondence, that if we would be stronger at mathematics, we could also apply it much easier to problems of the real world. Yeah.
So we have a lot of hints, it seems, that string theory might be onto something. It's one of these only theories that has this internal consistency, that does this anomaly cancellation. Yeah. We have ADS-CFT. We have, what was it? The gauge makes gravity. We have all of these hints that maybe it has something deeper to say about the nature of our universe. But is it still possible that despite all these connections we see, all these insights that we might get in terms of mathematics, that this is kind of just a beautiful, tempting mirage, and there's nothing related to the underlying nature of reality?
Absolutely. But I'll make a strong claim, which I believe. Imagine that we know that string theory is not the actual true theory of nature. I'm fully confident that even when the moment humanity knows, students in, 500 years from now will have to study string theory at university. Yeah. In the same way that all of our students study quantum field theories, which we know don't describe nature. As I said, the easier theory is this theory of stupid arrows pointing up and down, Ising model. It doesn't describe a magnet.
Or ones that have infinities in them that we sweep away so that we can, continue to do calculation.
Right, but it's more that's when it becomes a framework. Like what we know is this. We know nature is described by gravity in the form of Einstein equations. It's described by particle interactions in the form of Yang-Mills equations. String theory would go from a theory to a framework when it happens the moment you realize that, okay, it's maybe not what's behind nature, but it will always be a framework in case we want to understand Einstein's gravity better, or we want to understand Yang-Mills theory better, right? I mean, maybe I haven't said that, but what it has done for formal understanding of Yang-Mills theory is huge. There are people who don't care about what's the fundamental theory of nature. They just want to understand how do these Yang-Mills theories work that describe our particles. They turn to string theory calculations to understand it better. So
it seems what you're saying is kind of like when we use a spherical cow, or we do a calculation in dynamics without friction or without air resistance, it's still a useful framework to be able to get some insights, even if
string theory could be the spherical cow in the space of quantum gravity theories. Absolutely. And I will work with the spherical cow because it's usually easier, right? So
that makes sense. So here's maybe a slightly controversial follow-up then, is when, if ever, then should we stop pursuing string theory? People will say, you've been doing this for X number of decades and we haven't got as far as we would like to. When should we, quote unquote, stop doing it? Is it in 500 years when we have another hypothesis that has similar success? Is it when theorists get bored and decide they don't want to do it anymore? Is it when taxpayers get bored and say no more money for you? When do we say, no, we've done enough with string theory now, we're not gonna bother anymore?
So of the three options you gave, it's the first two.
Okay.
Because the taxpayer in the end, I hope that there's still some kind of a faith in, you have students that come to university, they already filtered out of, a group at high school, and you keep on being filtered, and so the people in the end
with the research, you're already interested,
right? And I think society has some kind of a faith that those people, let them do whatever they think is good. If I would be an investor, I would just, invest money, like just collect a bunch of smart people, and I don't want to, I don't want to tell them what to do.
I don't go to the hospital and say, like, treat my cancer like this. Like, I say, doctor, please help me.
Right.
Like,
Exactly. So I don't think the taxpayer will be the one deciding. I think it's, as you say, so either we get bored with it, and that means that probably there's some other framework which we find easier. And there's actually an example of this. So in the community that calls themselves string theorists, I think now there's a big chunk not working on string theory. Yet they keep on calling themselves string theorists. We organize conferences together. We have all the talks. And of course, Woit has used this tremendously to say, look, they're
people
giving
are
up.
Breaking away, they're giving up.
Yeah. It's not true at all, right? So it's, again, examples of propaganda. So this example, it's what people did is they picked up something that they left behind the moment string theory came to the fore. And this is called two-dimensional and three-dimensional gravity. So clearly the universe has 3 space dimensions and 1 time dimension. So we speak of a 4-dimensional universe. But people already knew that, okay, if I look at Einstein's equations in 2 or 3 dimensions, they simplify tremendously. And when I want to describe them quantum mechanically, they also simplify. And so people were like, okay, let's just do the spherical cow. This was in the early 90s and late 80s. And they said, okay, spherical cow can mean that we just remove 1 or 2 dimensions. Maybe we can learn already something. And then I think like 10 years ago, because of string theory techniques, another example, our community was like, hey, let's go back to this problem. Yeah. And they could suddenly solve it way better.
Yeah.
And so since then, there's like a huge amount of people that work on this. And the reason they still call themselves string theorists is because many of them have a string theory background. Yeah. And the computational tools they borrowed from what we learned from string theory. Yeah. And I think
you couldn't have just kept going with the old thing without having got the new tools. So it's a little bit disingenuous to just say, we did this, it was worthless, and then we went back. It's not. You're going back with a fresh set of eyes, a fresh set of tools, and then making progress on the
and those people, they're still following what happens with informal string theory, vice versa. And I think it only shows how people have an open mind. Yeah. And that there's no groupthink. Like whenever somebody says, hey guys, there's something cute, everybody's interested, even if it's not directly what you're doing.
And it's interesting, right, with the history, you mentioned that there was a piece of history there, but my understanding from listening to that Sean Carroll and Eric Weinstein debate on Piers Morgan is that string theory was kind of not looked on too well back in the kind of 70s. Exactly. There's a few people working on it, and it became popular because it solved problems, because it had this mathematical consistency, because it seemed to have these links within it. So it's not that theorists are just, oh my God, we just need to keep doing this. It's popular because it's jumping through these hoops, right? Because it's getting results.
Exactly. Yeah, no, 100%.
And if something else got similar results, you would jump ship, presumably, and work on that instead?
Of course. Yeah, of course. I think that's without doubt. Yeah. And I think we have many examples now, right? And I think for me, the most clear example is like the hype on two-dimensional, three-dimensional gravity. Yeah. And okay, maybe it's getting too much into detail. People now are interested in the question, could the lessons that we learn from 2- and 3-dimensional gravity, could it be that we are not allowed to extrapolate them to 4-dimensional gravity or higher dimensional gravity? And so at the moment, this is a key question in our field, where the two communities sort of, debate with each other. Yeah.
Interesting. So I want to come on to that point that you kind of mentioned there. And that's that some detractors of string theory and many online commentators that we talked about are under the impression, or they project the idea that string theory kind of dominates physics theory departments. It hoovers up an unfair proportion of time and money, and it's causing other ideas to kind of, wither on the vine. You can't, Eric Weinstein will say, this is the only game in town. You do this or you don't get a job. What are your thoughts on that claim? That
I'm so happy with this question.
Okay.
So it's not true. And even if it would be true, it's not a problem at all. So that sounds very weird, right? So, and let me tell you why. So people that call themselves string theorists, you would be surprised how many don't really know string theory. And that sounds bad, but it's not. And the reason it's not, so I think we said already before that, and everybody would agree, even these science commentators that or outreachers, that nature is described by Einstein gravity and these Yang-Mills theories that describe particle interactions. We just don't know how these theories look at arbitrary small length scales, right? That's where string theory comes in. Good. Now, what happens if you educate young people in string theory? What practically happens is that they become very strong in Einstein gravity and Yang-Mills theory. So whatever they do, it's anyhow what they need to know, right? So most of our students, if string theory would go wrong,
they would still have
so much of their papers will still be used. They will keep on using them, and those students they can teach particle physics lectures, they can teach gravity lectures, they can teach on mathematical topics. So I think it's super healthy for theoretical physics. But it is true. What is crucial is that we keep an open mind, and that anybody who is strong, and even if they don't believe in string theory and they want to work on something else, it should be completely fine, right? And so this projection that we're doing these extremely niche things is just wrong. Most of our students, they are just on a daily basis working with either Yang-Mills theory or with Einstein gravity. Maybe through the looking glass of string theory, but that's what they do.
So is this just people? Is this just theorists kind of marching with their feet? This is where the interest is. This is what seems to be the most promising, and therefore most people choose to work in it. Is that why people are still doing?
I would say so, and I would agree with some of them. It could be a huge issue. So imagine you find some theory for which the mathematical tools are extremely niche and nobody else uses it, and then you suddenly have a huge amount of people working on it.
Yeah,
I would also be worried.
Yeah,
but it's not at all with string theory. So right, I mean, yeah, as I said, the bag of tools is the bag of tools you need to be a good theoretical physicist, whatever you do.
I guess there is a slight concern though as well, and you mentioned this kind of on your Twitter, is that the funding that we get for theoretical physics is frankly ridiculously small, right? So you probably want, if there is even a perception that string theory is taking up more space, is the solution to that to give more money, to have more diversity of thought, to allow more theorists to explore more ideas, rather than just saying, throw string theory in the bin? Is it to allow that diversity, 1,000 ideas to flourish? Is that the way to go?
I think the way to go in science funding is that, and that's where my worry is. As I said, imagine you take the point of view from like an investor. You just want, you want money afterwards, right? And I think what we usually do is just give the money to the smart people.
Yeah.
They will do good stuff with it, and I'll get more money out of it. And so what I find very worrisome is that science funding is decoupled from what students want to do. So imagine, you have universities and they're like topics A, B, and C. And then you have the amount of students that go to topics A, B, and C, and especially take into account the level of competitiveness of those students. How strong are they?
Yeah.
It's completely not correlated with the amount of money that those topics get. Right? So, and in this sense, when you say theoretical physics is not funded enough, especially in this regard, it's crazy that I know it sounds arrogant and I hate it. I don't think theoretical physicists are better people, right? I mean, honestly, most of what's important stuff happening in physics are actually experimental things. But we do get some of the smartest kids every single year. And if I see how much they have to fight to get a PhD position, we're talking students that are, number one in the National Mathematics Olympiad, these kind of people, right? They have to struggle to find PhD positions.
Yeah.
And then there are other fields, maybe I will not name the names, where you have super average grades. You can start. and to me, that's not okay. Research money has to somehow be a little bit correlated to the quality of the students and the interests of the students. Yeah.
Interesting. Before we go into more serious discussion, I want to we'll clear the air a little bit. We'll have a couple of fun questions. So obviously we've talked about him a little bit here. So friend of the show, Eric Weinstein, he has some ideas about string theory which are maybe a little bit strange. So he claims that the Biden White House and the US government is really propping up string theory and keeping other ideas down. So I'd like to ask you, Thomas, how many checks have you received from the Biden White House, and why are you covering that money up?
Only a few.
Only a few? Yep.
Only a few, yeah. And they're on an account in Switzerland. So
so you'll never find them.
It's
what do you
crazy.
make of this idea that there's kind of a top-down, conspiracy to keep string theory as being the kind of the main game?
I don't want to become too political because I have a certain political inclination, but I am against the polarization that's going on nowadays. I think it's dangerous for society.
Yeah.
And I welcome people in my institute who are, conservative, right-wing, whatever. I'm all cool with that. But the thing I worry about is that something that we have seen in politics, let me not call it left versus right, let me call it populism.
Yes.
Fake news. It's exactly the people who started to invent the word fake news, who are the fake news producers. Lack of trust in experts.
You might have seen this. You might have seen this video we put out a couple of weeks called the rise of the science populace. It's very similar messaging that we're starting to see.
Exactly.
In science.
I think the Hossenfellers, Weinsteins of these, they're like the Trumps of science outreach. And I hope that their peak will go over because it's unhealthy.
Yeah.
Right. And I think originally, I think social media was a good idea because in a way, honestly, it gives power to the people. And in that sense, I like it a lot.
Yeah.
But this whole thing of algorithms where you try to optimize the number of likes and views, this has cost people like Hossenfeller, which I'm sure, and Peter Woit also were, maybe, there were like a bit rebellion in nature, but they were probably reasonable people at some point in their life. But once you start to get the likes from, the crazy people and they love your conspiracy, all these academics, they're, stealing our money and it's all groupthink. They don't know how to think critically. They're just stupid. They love it.
When you line them up side by side, it's amazing how similar it is. It's exactly the same.
Right.
It's
like Trump saying, I'm anti-government. Yeah. He is the establishment, right? Yeah. Again, I don't want to, people who want to vote right-wing conservative, fine. I think that's not what we're debating. We're debating honesty, objective truth, things like that. Yeah. And I think those science outreachers, they're just not honest anymore. And this is dangerous. And the fact that, again, I told you, the first hits that curious young minds get when they Google it, they get this crazy stuff. It's very dangerous. Yeah.
We're doing our best to push back, but it's hard work because, as you say, the algorithm is geared in their favor. So, it's a tough slog. So a related question is, and the second fun question here is, are theoretical physicists simply too scared to go up against the Voldemort of theoretical physics, Ed Witten? Is everyone so cowed by Ed Witten that they just do string theory? Because to go against his amazing mind, his insight, his genius, his brilliance would be unthinkable. Thomas, what can we say about it?
No, not at all.
No.
Right. So it's not that I know Ed Witten so well. I had a few email exchanges. I think I once met him at a conference.
Seems like a nice chap.
We had some conversation.
He's
extremely nice, and he's exactly the kind of person who would never want to project an idea like that. He's also extremely modest, so he would he's not the kind of person that, would tell young people, oh, you have to do this or that. No, he's the very opposite. And in our field, it is true. We're just so impressed by the smartness that sometimes, you get a bit shy or you're scared to ask a question, but not of the kind that you say.
Yeah.
Where
you would just do something you didn't believe in because he's so brilliant. Like it's not
right.
how science.
And to be honest, for instance, Ed Witten started writing papers on things that are not string theory at the moment also. And of course, Voit has said this shows that he's giving up. Like, not at all, but yeah, no.
Good stuff. Yeah. So I want to branch out into, as we come into sort of towards the end of this, discuss the popular perception of string theory. So we've talked about it throughout this discussion, but the popular perception of string theory online from these communicators we talked about is incredibly negative. Why? I want to get to the why. Why do you think string theory, despite being a small fraction of physics theory, has become such a target for hatred from non-experts, people who really know nothing about it? And I'm certainly a non-expert when it comes to string theory, but absolute non-experts. I'm talking about people who, have done no physics and YouTube viewers. Why is it the thing that everyone rallies behind?
I really wonder.
And hates? Why? What do you think are the main drivers behind that?
No, I think I know what you're saying. I even had it with a taxi driver in my own town who was like, oh, you work on string theory, but that's shown to be
bullshit.
Wrong, right?
That's it's been falsified. It's crap.
Exactly. Yeah. You go to a bar and a guy at the bar, he would say, oh, yeah.
Why
Indeed.
So this happened. Been able to cross that divide from physics to popular culture and still be, the devil, the worst thing ever? How has that happened?
I have a theory, but I can be completely wrong. So you don't.
I've got some as well. So let's share. So you give me yours.
So I think we in our field also made a mistake.
Yes.
And the mistake that was made was, I think, it was well intended. But let's wind back 20 years or even 30 years. As I said, when I was a young kid, like the books of Stephen Hawking, Brian Greene, especially Michio Kaku, they were super popular. And but what they did is I think they oversold it.
I think we've got the quote here in the. Yeah.
Did I say this before?
They promised the heavens and it never made sense 20 years ago. This was
There's even a quote that at some point, they say, oh, now that we have this mathematical tool called the Calabi-Yau space, something in mathematics, we will soon know the Calabi-Yau space that describes our universe and we'll figure it all out. Yeah. People actually said that. And I know some people who were there when those papers were written and said, we knew this wasn't true. But it was, I think, a combination of being so excited about all the developments, and you want to share your excitement with the outside world. But then some people took it too far, and now we're seeing the back reaction.
So people feel like they were oversold. I bought this, and now you've given me nothing, so I feel like I was lied to. Is this the kind of idea?
And so I think this back reaction, it's good. I think we needed critical voices. So I'm happy. In the end, I'm happy that people like, Rovelli, Smolin, in the end, that they stood up because somebody had to be critical.
Yeah.
But of course, the pendulum swung in the other direction.
Yeah.
So it's like nuance. It's difficult for people these days to find nuance and
I see a similar thing with particle colliders, actually, which is Sabine Hossenfelder's kind of weighing into. Is we said at the LHC we think we're going to find SUSY particles, we think we're going to find micro black holes, we think we're going to find extra dimensions, we're going to find all of these exciting things. And again, it was because people were so excited about the turning on of this machine. I can test these theories. This will be fantastic. And then they didn't appear. And now we go back and say, well, look, the Higgs is new. It's amazing. It's a completely new particle. We need to study it. And people go, but you said you were going to find A, B, C, D, E, and now you're backing up. Whereas it was the selling of it that was the problem. Yeah. And now we're paying the price for that.
And with that example, the Higgs for sure was reasons enough. We could have, it was super cheap. We found the Higgs. It's insane, right? Yeah. We found the Higgs for a little amount of money, in my opinion. So,
So the overselling is maybe a problem. I've got some other ideas, and I want to get your thoughts on these. Why maybe it's become the devil? Is is there a point that it's just a very easy method for these communicators to sell that string theory is incredibly complicated. It's one of the most complicated things that people can learn about. And it's much easier for these commentators, these populist commentators, to just say, it's all rubbish, it's all nonsense, you don't need to understand anything, just accept that. That's a much simpler message than go to university and learn about this for 20 years to understand what's going on. Right?
Well, I think it makes them look smart. Why? String theory had this name of being one of the most complicated things. Only Ed Witten could understand it. It's what they also said about Einstein's equations at some point. Like, nobody can ever find a solution. People did it a year later, but okay. And so string theory had like the thing around it. It's only for the smartest people.
Yeah.
So having an opinion about string theory makes you look very smart. No, honestly. And if you then go against it, people must say, wow, this person must be so smart. Right? I even met like people completely in other fields. Let me, the typical image of, highbrow, whatever, business guy on a reception after a few drinks, they would be happy to say that they think string theory is wrong. And then you probe them a bit and they just collapse, right? So, but it makes you look like interesting and smart.
And it plays in, like you said, to this populist idea. The experts are stealing your money. They're making castles in the sky. It's all bullshit. Like, I don't want to pay for this. It's the same kind of messaging, isn't it?
And I think they have seen with certain political directions that it's successful. This strategy of calling others bullshitters, people are against you. It gives you fame.
One more idea I've got in here is that theoretical physics has kind of slowed down, and this is natural because we've made such progress over the 20th century. Is there an idea here? Because you will hear from Eric Weinstein, you'll hear from Sabine Hosfeld, nobody's done anything worthwhile for the last 50, 60, 70. It gets longer every time you hear it. And there's a natural slowing down because the low-hanging fruit has been picked. Is it that people also want a kind of reason for that non-linear scale, right? Is it that they want an explanation? They want somebody to blame for there being this kind of slowdown as we've moved into the 20th century?
Maybe, but I also, when you say slow down, you have to be careful. It's usually in results that you can easily explain to the public.
Fair.
Right? So a particle, people understand, like they have a notion of fundamental particles that, wow, they found a new one. Wow. Yeah. And okay, that stopped, right? So apart the Higgs, there it is.
Which again is natural as the energy goes up, it becomes more difficult and blah, blah, blah.
Exactly. But I don't think I would agree at all with theoretical physics having slowed down so much. Okay. You have to look at all of theoretical physics. And one thing that I think has happened, and somehow the message didn't go through, cosmology. Cosmology became a precision science. It's fundamental science. It goes to the heart of also what's the fabric of space and time. We have the cosmic microwave background. We've never been able to see it at this detailed level. These are advances of the last 20 years. Yeah. Some people call them more important than the particle physics discoveries. I'm not sure I agree, but I would say they're equally fundamental.
We can let them have their Nobel Prizes now. We had ours in the 50s, 60s,
exactly.
70s.
And they're getting them, right? So there's lots of Nobel Prizes going to cosmology, to black holes. So, I mean, we have the picture of a black hole.
Yeah.
I think, no, a lot of things have happened. And also purely on the say the technical side, theoretical physics is a theoretical field. The advances are huge, but how do you explain this to the public?
Yeah,
like, hey guys, we have techniques to solve a strongly coupled gauge theory. They say, what? What did you? No, but you cannot explain.
No. I mean, I see it. Look. I'm working on YouTube doing in particle physics. It's hard. It's very hard, especially when somebody on the other side is saying, it's all bullshit. You don't need to listen. And the algorithm is working in their favor. You're absolutely right. So what I wanted to ask is, and I'm pretty sure your answer to this is definitely yes, is this people not liking string theory? Is this just external noise, or is it a big problem for the field, for its future, for getting people to come into the field? What are the impacts of this perception and this messaging from the people you mentioned?
My biggest worry is what it does to the youngest people. Okay. So I'm talking teenagers.
Yeah.
And what they will decide to do with their future. You have to think, I mean, people with a brain say between 12 and 18 years old. That's very important, 6 years of their life. Whatever tickles their imagination will, influence what they will do with their lives.
That's why I do particle physics shows for 12 to 18, because
Exactly.
if you don't have them interested by then, they've made decisions, they're away. You're done.
Exactly. And so that's my biggest concern. And the fact that if I Google it on different computers with different cookies, independent of my searching, whatever, I get the crap. I get the bad things. And so this is my biggest worry. But then, of course, you can ask, what about you? And that I find very difficult to judge. But the thing that I also tweeted was, when we get grant referee reports, so these are like, people saying, oh, you are applying for money for this problem.
Yeah.
And then there are external reviewers telling you whether it's a good idea to give you money or not. That's when I've seen some of these things happening.
These talking points starting to kind of come through into the site.
And people would say, you're just frustrated. You don't always get the money that you're applying for. Yeah. No, I can honestly say, hand to my heart, that if they would write, we don't think your CV is that good, I'm totally fine. Like, of course, we're applying with many people. I should not get it every single time. No, we get the weirdest stuff, like almost taken directly from Sabine Hossenfelder, like at the level of her tweets.
Yeah.
Like one person saying, you want to study microstates of a black hole? Well, you should first study the microstates of, and then they name one of the black holes that we have measured. Like, what are you saying? Like, what? I don't know. Just crazy stuff. And then indeed sentences like, but isn't string theory wrong? You write something about string theory, but it has been disproven. I mean, these things happen in my referee reports. Yeah. So it's a judgment of the field instead of the project, based on misinformation. And I understand it. I think the problem with these, I also have 33 grants. And I decline grants that I have to referee, which are outside of my field.
Yeah.
Because I feel like they say, no, at your age, you should be able to do it. They say, no, I mean, I don't feel comfortable enough. Yeah. It's too complicated. It's too nuanced. Yeah. I don't want to give my judgment here. Yeah.
That makes sense. So let's. I've got two more questions, and then because I need to let you go. You're a busy family man as well. I need to let you to get on with that. So let's go to a bit more of a positive image. We talked, everything is terrible. Everything is a problem. Let's have a more positive ending. So how can we improve the image of string theory? Will it just remain the same until we get any sort of experimental verification? I know there are people working in kind of string phenomenology. There's people still doing work to try and make contact with, the low energy scale. How can we improve that popular perception?
So I personally don't want to say anything about improving particular string theory. I think that's not what we should do. We improve the perception of string theory. We have to improve the perception
of fundamental
curiosity.
Yeah.
Fundamental questions. Like, I don't care whether in the end that goes to string theory. No, it's all about, are we allowed to be fundamentally curious? Why has the electron the mass it has? Why is dark energy everywhere, but it's like the smallest energy density ever measured? Whereas, if it would be any different, of course we would all die, but maybe that's not the answer to the question. Like, I think we need, especially, again, I want to repeat this for the younger generation, that there's another reason I'm very worried about this. So all of these things like theoretical physics, it's abstract mathematics. So it is a pain to study. Also for anybody, it's a pain. And what you don't want with the younger generation, now that you have all these tools to do whatever, is that they always look up their comfort zone. You need to intellectually not find your comfort zone. You need to do the opposite. You need to suffer, okay? And because it's like in the gym, you lift heavy weights, you're in pain, and afterwards you feel happy. And it's the same. So I want young kids to just study difficult stuff. And especially stuff which, comes from being fundamentally curious about how nature works. And that should be our main concern. Whether that means string theory or not, I think is less important. If you can solve that problem, whatever, I believe it will be good for string theory. But that I don't I don't have an interest in propagandizing string theory. I think there are some people who are excellent at it, who give very good arguments, like Kumron Vafa, I think is somebody who's extremely inspirational as a speaker. He tries to explain large audiences that all of these things are wrong, and he tries to explain why there can be actually measurable things. So I would advise people, check the public Kumron Vafa talks, and let us just make sure that young children, if they're fundamentally curious, we push them to study difficult things.
This is absolutely, I completely agree with you. And this is the thing that frustrates the hell out of me with Sabine Hossenfelder. So she's kind of moved on from particle colliders are just looking for ghost particles made up by theorists. She's kind of moved on now and realized that actually a Higgs factory is going to make something, we know where it is. So what's my line for that? How can I say that that's also terrible? And now it's, the Higgs is boring, it probably will just act like the standard model says it does, and it's too expensive to just, check these things. It's like, well, checking the most important central particle of the standard model is science. It is being curious.
Absolutely.
It is working out what is actually going on, making sure the Higgs potential has the shape we think it does, making sure the couplings are what we think they are, checking the Higgs width. Are there particles? Is it decaying into things that we can't even see, but we can infer that they're there? If your stance is it's boring, it's too expensive, that is a fundamentally incurious stance, right?
Absolutely.
Especially when taxpayers are saying, we will pay for it. The ROI is not too bad. Actually, we are interested in these kind of things. It is a fundamentally incurious stance. And then you're pushing your line to try and make political pressure so that these things don't happen.
Yeah, it's horrible. And what I think she doesn't appreciate is, and that's more your field, but so CERN, I've been told, is the most complicated machine ever made by humans.
I can't believe it ever worked. I don't know. Have you ever been downstairs at the LHC?
I've been downstairs.
I've never seen so many wires, connections.
Exactly.
I'm surprised my computer works half the time. I do not understand how they get that machine to work.
But think about it like that. So CERN, the Large Hadron Collider, is the most complex thing ever built by humanity. So to me, it's like, of course, things. You will learn things on the way. Like, even if it doesn't pan out, if you just have a bunch of people, like thousands and thousands, working collectively to make some complicated measurement possible, that by itself, I'm pretty sure is worthy. And in the end, I don't think it's even relevant that from that point of view that they find something. Like, are you able to get these energy scales, this refinement in your experiment? You learn things which will be relevant for anything else. Right. So no, humans need to do these things. It's good no matter what happens. Yeah, absolutely.
Absolutely. And the last question, because I know I need to let you go, is let's talk about the future. What are the big focuses now in string theory at the moment, and where are the next breakthroughs going to come? I saw something on Twitter about this de Sitter space solutions and these kind of things. What are the big things that are happening, and where are we going to go in the next kind of few years, do you think?
Okay, it's difficult to talk for such a big field with so many different directions. So I'll just speak out
your personal ideas,
which maybe the one which is a little bit related to yours, to the one that you're showing here. It's what I believe actually is a direction that Kumron Vafa is pushing. That let us try to understand the dark sector, which we know is there. So that I think should make us excited, whether you're a string theorist or not. We look into the universe and we realize there's a dark sector. So again, dark sector means we indirectly see the effect of certain things. It's called dark matter, dark energy. We don't understand it. I am convinced that any breakthrough in fundamental physics, be it string theory or not, completely depends on this dark sector. And we will know the answer. Because, the stuff is out there. It is just filling our galaxy. And so it's here. It's maybe, in small density in my own room here. So I believe that whatever happens, I think it's a dark sector and we need to understand it. We need to do precision experiments, not necessarily high energy, just precision experiments. For example, there are precision experiments of checking Newton's law of gravity at extremely small distances, because also the dark sector has an influence on that. So this is exciting, but I do agree that unless there's a huge mathematical development, maybe AI can do it, I don't know. It will come from experimental input in the end, and then I bet all my money on the dark sector, which doesn't necessarily require high energy skills. Yeah.
Superb. Thomas, I think we will leave it there. Thank you so much for taking the time to discuss all those things with me. I will make sure that your links are down below. Some of the things that you mentioned, the Vafa's talks as well, I'll make sure they're down in the description. Are you off to go lift some of those Leuven branded weights plates now? That was very, very special. That
I did that before this podcast.
Why does your university have branded weights plates? This is amazing. This is a level above.
I support it.
Yeah, me too. But Cambridge didn't have these, I don't think. I'll have to check.
Yeah.
Amazing.
No, it's one of the good things of my university. Yeah, fully endorse it. Yeah.
Thank you, Thomas. And
it was
hopefully the next time, or when the big string theory breakthrough comes, we can get back together and have another chat.
For sure. Thank you so much.
Thank you very much, buddy. I really appreciate it. Take care. Have a good evening.
Yeah, you too. Take care.
Bye now.
I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.